Swayam Prabha. Digital India. Educated India.
Welcome everybody. We're going to talk about hydrations of alkynes. Hydration is just taking a sip of water. We're going to take water and dump it across a triple bond and see what we get. And so that's what this means, hydration. Just like when you are thirsty, you go take a sip of water, molecules do the same. And they don't just do it like in one shot, they do it in multiple steps. This one especially has a lot of steps, okay? So just follow along and then you could practice on your own later. So if you have a terminal alkyne, you have a hydrogen here. Now when you have a hydrogen, hydrogens don't really donate electron density as much. So therefore these pi bonds here aren't very nucleophilic. So you need to have a catalyst. If you just add H2SO4 aqueous, it's really not going to do the job well. We need to have a heavy metal catalyst. And what do we usually add? We add mercuric acetate. So that's AgOAc twice. Here, Ag is in a 2+ state because the OAc is just nothing but acetate. And you know acetates are -1. And you have two of them. So that's why you have a neutral molecule, mercuric acetate. Now, mercuric acetate is soluble in water. It's typically colorless, but if you leave it around for some time, it can get yellow. It's good to use it fresh. So here's your mercuric acetate, and we're going to use that to then kind of activate that molecule here. All right. Now, this is quite a bit to write. This is a terminal alkyl. I'm going to just put an R for this. So we're going to do the mechanism here. So it's R, and then you have a triple bond H. Now it can be anything. In this case, it's just that, because I just want to have a number for you for your product, and you're getting 91% of your product with mercury. So that's pretty significant. Let's see what mercury does. Mercury is a huge atom. I mean, carbons are tiny compared to this big mercury. So you have a mercury, and mercury would have 2 acetate groups. And these are going to just hang around for the ride. So mercury here can be electron deficient, that's your electrophile. It pulls up that pi bond, but because mercury is so huge, it doesn't go on this end or this end, it just sits plonk on top of that pi bond. So the pi bond goes over here, and the mercury catches that too. And so now that's too much for mercury. One of these is going to leave. So you would get R, C, H, and your pi bond breaks and goes over to the mercury. The mercury is going to have one acetate holding on to that. And this is, I'm going to write this as OAc. And you are going to have this, and you'd have a positive on that mercury. One of your acetates has left. And now you're going to have this transition state kind of gel into an intermediate where your dotted lines become solid lines. And so this is a syn addition. So initially your addition is a syn. This is a syn addition. Okay, so which is why I made it stereo specific. Now let's look at what happens to this molecule. You can see it's not symmetric. You have an R group here and a hydrogen here. So electronically they're different because hydrogen doesn't really donate much electrons into this. Sterically they're different because hydrogen's teeny and R groups can be huge. So in both ways, this molecule is not symmetric. So you can get regioselectivity because this region is different from this region. You see, so you got regioselectivity. Let's say you bring in a protic solvent like water, the simplest of them all. Where do you think water is going to insert? Do you think water wants to attack here, or water wants to attack here? Now, water is a small molecule. So where do you think water is going to attack? Well, think about it. This is positive, which means it's pulling electrons here. Therefore, you're going to get a delta plus here and a delta plus here. You're in a protic environment, so these are polarized bonds. Where do you think you're going to have more stability for that incipient positive when this mercury leaves? Mercury's got to leave at some point. Do you think you want to break the mercury here by attacking with the water here? So you have a delta plus here, right? Because it's tugging. You also have a delta plus here. Who's able to handle that delta plus better? Right? We talked about it and we even did the alkenes. When you have R groups here, they are going to support that incipient carbocation. It's not a full carbocation. If you had a full carbocation, you'd really have no stereospecificity, but you do have a stereospecific attack here, and that's maintained. However, these bonds are being pulled by that mercury, which is a positive. So when you have more R groups, you're able to hold up well. Whereas if you had hydrogens, you're really getting no support from that hydrogen. It's just got a 1s electron. What can it give? There's nothing to give there. So therefore, the positive is supported more here than here. That's why it's regioselective. So in the terminal alkyne case, you do have a difference between the termini. So you do see regioselectivity there. This flips over now, and this is going to be attached to a water, but water lost its lone pair, so it's a protonated or positive hydronium ion. Mercury rolls over, and it's still got the OAC hanging on to it. And now we got to see how to get rid of it. Well, first things first, you got a positive on the oxygen, you got plenty of water here because the sulfuric acid is aqueous. Whenever you see sulfuric acid, think of it as hydroniums, H3O+. So the water molecules are surrounding it, and so that's going to deprotonate this. Now, what would you get right after that? You are going to get a OH right next to a double bond, and we had a special name for that. Do you remember what that is? When you had an ene and an ol. It kind of gives it away. What is it? It's an ene-ol, all right? So whenever you have an ene-ol, just like the name says, ene-ol, they hate being in that position because these lone pairs are butting into these pi bonds. So in order to relieve all that repulsion and strain, they go over to the keto form by forming a double bond. But you know that's too many for that carbon to handle. It's already got a handful. It's got 8. So it's going to pop off one of those pi bonds, and those pi bonds are going to then get protonated by, well, what do you have? Just H3O plus again. So the H3O plus here is really busy running back and forth. So now you got a protonated carbon over there. So you have, and all of these are reversible. And in a lot of the cases, I know I'm not putting these reversible arrows, but they are. But hopefully the reversible arrows are more towards the product than the reactant, otherwise you'll never get there. So here's your oxygen. You lost a lone pair, so you have a positive. And you have a hydrogen now from the water. Now, obviously, the mercury is still hanging on, and the molecule is not very happy about this intruder. I mean, how dare a metal get on in a hydrocarbon, right? They don't really belong in the hydrocarbon family. You got to find a way to kick it out. Well, this is a plus. It's going to be pulling electrons. It's going to be pulling these electrons, and it zaps these electrons from this mercury when it's not looking. So mercury, well, bye-bye. We need your electrons, but we don't need you. So get out of the way, and let's make sure that we have everything we need to be happy. Let's see, we have a double bond here that makes it really very nice and comfortable. However, we're back to the same old conundrum of having a pi next to a lone pair, which means it's an ene-ol. not good. So enols, we got to get rid of them. And how do we do that? This time your enol is going to do pretty much the same thing in all. Somehow students have a hard time remembering this enol. It's just what the name says. And here your mercury, it kind of takes off on its own. It's back again to Ag plus OAC, and then it gets hydrolyzed, and it's kind of a bye-bye at that point. Now, we don't want enols. Enols always go to keto form. So let's protonate that. So over here, you want to go to the keto form, which means there's too many here. And this is then going to get protonated by H2SO4. Well, in this case, let's just say hydronium. If you have H2SO4 water, you're bound to have that. So now you're going to have this molecule come over and give you a very nice carbonyl on one side. However, there's a positive and a hydrogen. Now, well, we're one step away from our product. We got to get rid of this positive. And when you have water, in this case, you also have acetate. So acetate can come in. And if you look at the pKa values, acetate is about 4.5 for the acetic acid, and H3O plus is about -2. So stronger the acid, weaker the base. Weaker the acid, stronger the base. So we can use acetate here to pull this off. And we are going to get a carbon that's got a double bond. And so that's a carbonyl. Since you have two carbons flanking that carbonyl, that's called a ketone. So earlier with borohydration, you got an aldehyde, mercuric acetate hydration or acid hydration, you are going to get a ketone. So there is a difference between the two methods. Now, another thing is you have a methyl ketone. If you start with a terminal, you would always get a methyl because this carbon doesn't have a chain. It stops right there. And you're hydrating it, so you're going to get CH3. So this is a methyl ketone. So you are always going to get a methyl ketone as your product. It's not going to be an aldehyde like in the borohydride reduction. Another thing is it is stereospecific because you are going on one side and then attacking from the other side. So you have a syn addition initially, and that is followed by an anti-addition. So overall, it really doesn't matter because we lost any kind of stereochemistry here. But just to keep things straight, this is stereospecific for terminal alkynes, syn followed by anti-addition. And there's a lot of enol keto tautomerism. So you do that over and over again. Here's your enol keto, enol keto. So you get a couple of tautomerisms going on here to get you a methyl ketone. The first time you do that, you are going to have a protonation, and the second time also you have protonation. I put those in different colors, but it's just all protons. So here's a methyl ketone that you get for terminal alkynes. All right, what if it's internal? Do we have anything different? Let's look at it. For internal now, you have two R groups that can donate electron density into this. Therefore, these pi electrons are quite nucleophilic. So internal alkynes are more nucleophilic than terminal alkynes. So we don't always have to have mercuric acetate for this, but it would speed it up because it's a catalyst. Now you could see that triple bond, pi bonds, the first pi bond is actually a lot easier to break. We have two carbons holding on to 6 pairs of electrons in the center. So once you take one pair of electrons and react them, then you have two carbons holding on to 4 electrons, sigma and pi. So now it's getting a little tighter. So you can see alkene pi bonds are a little harder to break, need more energy than alkyne pi bonds. So we can take these and you could also react them without mercury. Since we did a mechanism with mercury, it's going to be pretty much the same thing here. So let's try to do one without the mercury, shall we? It's going to be a little simpler because you don't have so many steps. So here's H2SO4 and water. You don't want to use HCl or HI or HBr because those halogens can attack the pi bond. So let's do a mechanism for that. Shall we do that without your mercury this time? So once you have H2SO4 and water, it's basically hydronium ion. H2SO4 is just going to be sulfuric acid, and that gets protonated with water. Let's say for the first step, this is going to reach out and catch that proton here. You are going to get a vinyl cation. Vinyl cations are bad. And you get protonation here. And your HSO4 minus bisulfate, hydrogen bisulfate goes away. Now, this is going to be a very, very unstable cation. Secondary vinyl cations are less stable than secondary carbocations, and they're even less stable than primary carbocations. So they're very unhappy. And so as soon as this forms, it's going to then react with water. Water will come in and zap it up. So it's not even there for, a microsecond. It just immediately gets zapped up by water. So now water is going to go in and form a hydronium, and that is going to then become deprotonated because it doesn't really want to be positive. So you have more water in there, and your water molecules are going to come in and neutralize them, make them neutral. So then that is going to go over and become an enol. We saw this before. So here's your ene and here's your ol. Well, enols aren't really that very happy by themselves because, as I said, there's some repulsion here, so there's some strain there. And so they want to go to keto form, so they'll come back and push that pi bond out, and that pi bond can catch a protonated water, or it can catch a sulfuric acid, and it is going to get protonated. All right, so it gets protonated right here, and so now you would have a single bond here instead of a double bond, and you would have a hydrogen here that is going to be from the hydronium. This is the hydrogen that you added earlier from the acid, so you now have two hydrogens here, and you have a double bond here that is now almost a carbonyl, and carbonyls are very, very stable functional groups, and so that's where it's going to stay. That's the home. It's reached there. However, that little proton is kind of bothering it because it's not neutral, and so you can deprotonate that with water and get your product. So your product here has got H, 2, and O. So you see the entire time what we were doing is adding water one atom at a time. Hydrogen, then oxygen, then hydrogen, and we are home. All right, so that's about 80% there. We can speed this up by adding mercury. Mercuric acetate will speed up reaction, and mechanism is exactly like this. Now, when you have a symmetric alkyne, then you're going to only get one product, because whether you put the oxygen here and the hydrogens here, or you put the hydrogens here and the oxygen here, it's going to be exactly the same. So you only get one product. However, if you have an asymmetric alkyne, well, now you have choices. You can put your oxygen here and hydrogen here, which is what you're going to get here, or you can put your oxygen here and hydrogen here, which is what you have here. And there's equal chance of doing either one because both these carbons are equally nucleophilic. You've got R groups here and R group here. So it's about a 1-to-1. So there's really no regioselectivity here. So internal alkynes are non-regioselective in adding water or undergoing hydration reactions in acid. However, they are going to be stereospecific if you are adding mercury. In the presence of mercuric acetate, they would be stereospecific. Syn stereospecificity when you're adding mercury. And here too, if you add mercury, this is going to be syn stereospecific. And most of the time when we do these reactions, we do add mercury. The only reason I wrote this out was because some textbooks have it without them. And so I just wanted to show you that you could do it both ways. But this is definitely going to be a lot faster and better yield if you add mercury here. You'd get side products from, the other regioisomer. But for the most part, when you have mercuric acid, you're going to get a pretty decent yield. All right, so we're going to come back with more regioselective, stereospecific reactions. Stay tuned, guys. I will see you soon. Bye.